So now I just want to remind you of two common inverse functions, which are the exponential and log functions, which you've studied in the past. Remember that the exponential function is of the form f of x equals constant to the variable x, where a is greater than 0. And the log function is the inverse, so I'm going to use this notation for that. Remember, that's the inverse notation, log base a of x, where a is greater than 0 and a cannot be 1. And since these functions are inverses of each other, that means that this statement is true, which means when we apply that a to the log base a of x will equal log base a to the a of x, which will equal x. Okay? And then there's a whole list of other properties of logs that you're aware of. Now what I want to do now is I want to introduce the natural exponential and log function, which is a specific exponential and log function with a base of a constant of e. So the natural exponential function is an exponential function with a base of e, where e is approximately this irrational number 2.72. Okay, so f of x equals e to the x, and that graph would look the same as an exponential function in which you had a growth situation in which the constant was more than 1. So it would look something like that. Three important features. You have the horizontal asymptote on the x-axis, you have the graph passing through the point 0, 1, and this is the point 1, e. Okay, so this is the natural exponential function. We'll talk more about where this number e comes from later. Just on your calculator, if you wanted to graph this, you would find e here, e to the x, and you graph it. And it's an exponential function. All right, the natural log function is the inverse of the natural exponential function. So therefore, just to go through the steps here, remember inverse means switch x and y. To isolate y, we can write this as y equals log base e of x. And now we have a special notation because natural logs will be very useful and common for us to use. We have a special notation for this, which is ln x. So ln x is your log function with a base of e. And if you graph it, you're going to have a vertical asymptote on the y-axis, and you're going to have main points at 1, 0, and e, 1, which is 2.7-ish, 1, and the graph's going to look like that. Okay, the two graphs, remember, are reflections of each other about y equals x. On your calculator, ln, okay, notice log and ln are close together. ln, just a special type of log, log, log base e of x. So ln x brings up our graph. Okay, and again, because the two functions are inverses of each other, that means applying one after the other produces x. And all of the other properties of logs that apply for common logs or other base logs, logs, apply for ln. So for example, ln of xy is ln x plus ln y. Remember that x and y are both positive because you can't log negatives. What other properties are there? Log x over y is ln x minus ln y. Another common property, exponent, is n times ln x. Change of base rule, which says we can change to any base by doing this. So we could change to base b if we wanted, as long as b was greater than 0 and b was not 1. And so we could certainly then change to base e, which would make that ln x over ln a. All right, let's just solve a couple of equations involving natural and exponential functions. So we have the log base e. We have the ln of 1 over x equaling negative 2. And so to get rid of ln, we know that if we have ln x and we raise it to the e power, that undoes the effect of the original ln. So I'm going to take this expression and raise both sides to the e exponent, which is 1 over x. And so x is 1 over e to the negative 2, which means x equals e squared. Remember, with log equations, we have to check to be sure that we're not doing the log of a negative value. Well, e squared is 2.72 squared. That's positive. 1 over positive is positive. Log of a positive should be possible, so should be okay. Therefore, answer is x equals e squared.